Here I've abbreviated average atomic mass as AAM. In other places you might just hear the term atomic mass or atomic weight, but those two terms mean the same as what I've called here average atomic mass. The average atomic mass is the weighted average mass of all atoms of an element measured in AMUs. For an element with various isotopes, here's the equation for calculating average atomic mass. Average atomic mass is the mass of one isotope multiplied by its percentage plus the mass of another isotope times its percentage, where those percentages are called the percent abundances. And when you're using this equation, you're going to want to use the decimal form of the percentage. For example, you would use 0.253 for 25.3% or 0.071 for 7.1%. So once you've got the percentages, you want to make sure you move the decimal 2 places to the left before you use this equation. Now in the equation I've shown only two isotopes, isotope A and isotope B. But depending on the element, you might have to do more in this equation. For example, titanium has 5 naturally occurring elements. So you would have to go mass of A times percent A plus mass B times percent B plus mass C times percent C, etc., all the way up to a total of 5, which would be like mass of E times percent of E. So let's try a couple of examples. Lithium has 2 isotopes. Lithium-6 atoms have mass 6.015 AMUs. Lithium-7 atoms have mass 7.016 AMUs. Lithium-6 makes up 7.5% of all lithium atoms. Find the average atomic mass of lithium. So here's our basic equation. We're looking for the average atomic mass on the left. Notice that because lithium has only 2 isotopes, we only have 2 terms on the right side of the equation. Mass A times percent A, and then the other term will be this one, mass B times percent B. So, what do we know that's given in helping us calculate the average atomic mass? Well, we know the mass of one of the isotopes, 6.015, and we know its percentage. So notice here that I've put the percentage in decimal form, so I've moved the decimal 2 places to the left. We also know the mass of the other isotope, but what is not given is the percentage of that isotope. But if there are only 2 isotopes and one of them is 7.5%, then the other, you see, must be 92.5%. So sometimes information like that is deliberately left off because whoever's asking the question is hoping that you will think and figure out that if one isotope is 7.5% abundant, then the other must be 92.5%, because those two must add to be 100. So now it's simply a matter of typing this correctly into your calculator and finding the answer. So we're going to multiply these 2 terms, we're going to multiply those 2 terms, then we're going to add those, and this is the answer we get, 6.94 AMUs. Now, there are 0 atoms in the universe of lithium that have this mass, 6.94 AMUs. Because if you're a lithium atom, and very few of you are, but for those of you who are lithium atoms, you know that you are either possessing this mass, 6.015 AMUs, or you have this mass, 7.016 AMUs. However, that number is still very useful, and notice that it is on the periodic table. That number, 6.94, for lithium on the periodic table refers to 2 things. It refers to the molar mass in grams if you're talking 6.02 times 10 to the 23rd atoms, but that number is also the average atomic mass if you're talking one average or one typical atom of lithium. So, what I'm saying here is that the periodic table has been rigged such that this decimal number has two meanings. You put grams after it, it's the mass of 1 mole, or 6.02 times 10 to the 23rd of those atoms. If you put AMUs after it, it's the mass of one average or one typical atom. Let's try one more. We need to fill in the two empty blanks on this table. The percent abundance blank is going to be fairly easy to figure out because the sum of these three percentages must add up to 100%. Silicon has 3 isotopes, so that sum of that column must be 100%. The next one is a little bit more problematic. We might be tempted to say, oh, well, it looks like there's a pattern, and so the mass of silicon 30 is going to be 29.98. But we can't know that for sure, so we have to check. So let's use the equation for calculating average atomic mass. Notice that the right side of this equation has 3 terms, A, B, and C, because silicon has 3 isotopes. Let's fill in the values that we know. We know the mass of one isotope and its percentage. We know the mass of silicon 29 and its percentage, but we don't know the mass of silicon 30, so I've just put X there, but we do know its percent abundance, 3.1%. So again, I've put all those percentages in decimal form. And we don't know the left side of this equation either. So this equation is not helping us at this point until we realize that when we look at the periodic table, the average atomic mass, which is the left side of this equation, is actually shown right there on the periodic table. So 28.086 is the left side of this equation. Now we're ready to go. We have one equation with one unknown, and it's simply a matter of doing the algebra correctly and getting our answer. So I'll go ahead and show my work here. We're going to take this product and that product and that product. Notice that I've simplified those. We're going to add together the 25.806 and the 1.353. Then we're going to subtract 27.159 from both sides. And now we're left with 0.927 is equal to 0.031 times x. So we're going to divide both sides by 0.031, and we're going to find out that x is 29.90 AMUs.